How do you do, ladies and gentlemen, and boys and girls and teachers? I'm Julius Sumner Miller, and physics is my business. And my business today, making more noise, I suppose, or sound, or some such. More exactly, this business of resonance and forced vibrations. Consider the following, which I tried on an earlier lesson to do, but with not too much success, for some reason. About this, I should say more. You know already my philosophy. Experiments, demonstrations never fail. For nature to do what you want her to do, you must make some very special, meet some very special requirements. If they are not met absolutely precisely, nature will not show what you want her to show. She will do something else. So if the experiment did not succeed in an earlier case, we'll try it again, but we are forced to think of why didn't it work before. Two forks, middle C, middle C. We hope they're identical. Hollow chambers, resonating chambers. I'm going to strike this one, quiet it, and we will hear that one. Why? This emits 256 pulses per second, which are fed into this one. This picks them up and is set into oscillation. Listen now. There it is, clear as the nose on my face. I'm going to do it again in the reverse order. Listen. There it is. Now, how far apart could this be made to happen? Oh, great distances. Because this is exactly what your ear does, and you could hear me at some great distance, I am sure. Resonance. Resonance. Consider now the following. I have here two cardboard tubes, one of which slips inside the other, so that I can change the total effective length. I am going to strike a tuning fork and hold it in front of this open pipe, which is so long, which has a certain natural frequency. I'm going to change the length by this sliding tube and hope to find a resonant length for this fork. Listen now. Yeah, there is a place. There is a place at which this length is resonant to this frequency. That's an open pipe. This end is open, that's open. Here is a closed one. Now, it would be an interesting exercise to compare the lengths of open and closed pipes for the same fork, but I leave that as an exercise for you. This is closed because it is closed on the bottom at the table. Listen. Uh-huh. Let me use another fork. This fork happens to be what? 512, that's an octave above middle C. Oh, I can't get a length there. There it is. There it is somewhere in there. Let me try this open one. Very clearly resonant. Very clearly resonant. Or, as I might do it, consider here. Here is a glass cylinder with some water in it and a lucite tube. And this is a closed end, so the air column here constitutes a closed tube. Let me show you resonance. There it is. Now, what can one do with this? By making certain measurements, we can determine the velocity of sound in air. Here is another tube, another fork. Oh, very clearly resonant. I hope if the tube is long enough to find another resonant length. Listen. Yeah, pretty nearly. I couldn't quite make it with the lengths available to me. Resonance, resonance. I want to show it to you in a more delightful fashion. Here is something really enchanting. A wooden frame which is hollow, so like the belly of a piano or of a fiddle. A tightly drawn string with two bridges, one here and one here, so that I have cut off a certain length of string this long. The string, therefore, has such a length, is under such a tension, and is so fat. Now that string has a certain frequency. Listen. It therefore has a certain pitch. It is resonant to a certain fork. Proof. I've put a little paper rider on there because if the string is vibrating, you can't see it. And I'm going to strike a fork and apply the end of the fork to one of the bridges, and we hope that the energy of the vibrating fork is communicated through its stem to the string, and if the string is vibrating, we would hope to see the little flag there quiver. Watch it now. Oh, yeah, I like that. Let's get tight on that again, boys, because I like that. And do you see, people, if I like something, well, I might do it again because I like it, and that's good enough reason. Mark you, I suppose I have done this demonstration 4,782 times, and it never fails to stir my soul because it is pretty and dramatic and spirited. Watch it now, watch. There it is. Now the question is, will this string respond to some other fork? That would happen to be B, 480. Let me try 384, which is G. Listen, watch. No. That string can vibrate 480 times per second in a natural, ordinary, comfortable, happy way. It will not vibrate 384 times per second. How about 426.6? Oh, yeah, that reminds me. I find a fork. On an earlier lesson, I suggested that, I said that A in America, the orchestral A, was 440 vibrations per second. And then I said that I thought that A in Europe was 426. I find it, 426.6. Now listen, watch. No. But 480, yes. There it is. And so we have that kind of behavior of vibrating strings. Consider now the following. Let me get this out of the way. A fork. I strike it. I deliver the stem of the fork to the table. What's happening? The table is being put into oscillation at the same frequency as the fork, which is 426.6. But the music it emits, the sound that emerges, has a little different quality to the ear. Sure, A, when played on the piano, sounds different from A played on the fiddle. So this has a different quality. But the table is forced into vibration that many times per second. Let's take 480. Listen. Let me try this table back here, which has more stuff on it. May have higher or lower pitch, I don't know. Very interesting. Now something quite enchanting. Consider the human voice, which results from the vibration of the vocal cords, the hollow cavity called the mouth, where the tongue is, where the teeth are, how the lips are held. That chamber, the vocal chamber, has a resonant frequency. And I have observed over the years that when I try resonance at the open mouth of boys, the response is to a fork of lower frequency than that for girls. Let me show you what I mean. Listen. Well, let me try another fork. And sure enough, this is 426 and that's 480. Let me try one lower, 384. Maybe I'm boom, boom, boom in pitch. Let me try a higher one, 512. Notice I have a strange vocal system. Resonance. Forced vibration. In certain places in the country, in New England, there are some wooden bridges still with signs fore and aft that say, no trotting of horses on this bridge. No trotting. Why? The periodic delivery of forces from the horse's hoofs might set the bridge into vibration and render it apart. Or consider soldiers in marching, crossing a bridge, they break up their stride. Now, where do we have some ancient, wonderful commentary of the same sort? If you read Joshua in the Old Testament, Joshua 6:20, it says something like this: the priests blew their trumpets and the walls fell down flat. And I've often wondered why the sackers of cities didn't just go around the world, the then known world, with bands and musicians playing music in order to fell the walls of the cities instead of attacking them with manpower. All right. Resonance, forced vibrations. Consider this, which is quite enchanting to look at. Here I represent the towers that carry the big, heavy cables in transmission of electric current across the country. This is a cable. It might be viewed as hanging like this. The shape in which it hangs is very special, incidentally. It's called a catenary. And if you look up the word catenary in a dictionary, you will find that it means chain. Now, when the wind is very high, this cable could be set into oscillation, which is dangerous for the mechanical system, as well as for the electrical affairs. Problem: we need to damp out that mechanical motion. And so what is done? If you look closely, next time you see these transmission lines, you will observe that there hang on the wires some system that looks like this, called a damper. Now what happens? When that cable is set into vast oscillation with large amplitude by a stout wind, the cable, having flexibility, as I will show you, takes up the oscillation and damps out the mechanical motion of the wire. Here it is. Here is a cable damper. The wire goes through there, and now you see these are flexible, and this takes up the energy of the oscillating wire. So I say this business of resonance, forced vibrations, mechanical damping, and the like, very enchanting to contemplate, and I would invite you to think more about it. So, more on resonance, more on forced vibrations. Mark you, all this evidence that the natural world presents to us is gotten by one of our senses, namely the auditory, and all governed by the reception that the eardrum gives to the variations in pulses. And I thank you for watching.